So here's the example where we use the modified definition. Given a function f of t of course would be time, equals 450 minus 4.9 t squared in meters, right? What we want to find is the velocity at 5 seconds. Okay, so you recognize that this is a free fall function. This is Galileo formula. This is an object falling from a initial height of 450 meters, and 4.9 is 1/2 g. Right? G equals 9.8 meter per second squared. So you have y sub 0 minus 1/2 or plus 1/2 gt squared. If g is negative 9.8, you end up having this expression. I believe this was in the lab, wasn't it? So now we know that the velocity is the rate of change, right? But the average velocity is the average rate of change. The velocity is the instantaneous rate of change. So here's we're going to use the following. We're going to say that v of t equals the instantaneous rate of change, or the IROC, of the position function f of t. And using our new definition, the instantaneous rate of change graphically is the slope of the tangent, and therefore it will be f prime of t. In particular, v of 5, the velocity after 5 seconds, will be f prime at 5 seconds. Okay? Again, the velocity is the rate of change. The velocity of a function, of a position function, is the instantaneous rate of change. The instantaneous rate of change, if you graph position versus time, the instantaneous rate of change will be the slope of the tangent. The average rate of change will be the slope of the secant. So, the slope of the tangent, by definition, is the derivative, f prime, and therefore we need to calculate f prime at 5 seconds. And we use this definition to calculate it. And so, here we go. By definition, f prime at 5 seconds will be the limit, and I use this, so h goes to 0, of f of 5 plus h minus f of 5 divided by h. Okay? One thing you're going to realize, with this modified definition, a lot of time it's convenient, because instead of dividing by a binomial, by x minus a, you divide by a single term, by a monomial h, which is easier. So, how easier? Hopefully, we can evaluate and manipulate the numerator such that h will be a factor of the numerator, and then we have reduction. H in the numerator will be reduced by h in the denominator. And most of you already discovered that in the lab. So let's see how this pans out. So the limit as h approaches 0, and now I'm looking at the function 450 minus 4.9 t squared. Instead of t squared, 5 plus h. So the first expression will be 450 minus 4.9 times 5 plus h squared. Right? This will be f of 5 plus h. And then f of 5 will be simply 450 minus 4.9 times 5 squared. Like so. Okay? And all of it is divided by h. Now, this is a number, the second part, f of 5, I could have calculated ahead of time, but it's 4.9 times 25, 450 times minus that. Actually, we'll have some simplification here. Let's see how this works out. The limit, it's easier, instead of writing by h, having a very long fraction bar, I'm going to multiply everything by 1 over h, which is the same thing. Okay? Just will save me the need to use a very long fraction bar. And now, what I see right away, that 450 minus 450 going to cancel each other, so I don't need to mess with those. Right? So what I have is, after reducing 450 and 450, I have 4.9 multiplying this binomial, and I have 4.9 multiplying this monomial. So I'm going to factor negative 4.9. Actually, I'm going to factor just positive 4.9 at this point. Okay? And what do I have? From here, I have 5 plus h squared. Well, that will be 5 squared plus 2 times 5 plus h plus 10h plus h squared, right? And then here I have plus 4.9 times 25, like so. Okay? First of all, again, the 25 and 25 are going to cancel out. It's plus because double negative, but it really doesn't matter. I have 4.9 times 25 and 4.9 times 25. So what I've left here is the limit as h approaches 0 of 1 over h, and I have 10h plus h squared. So I factor out the h, and I end up having 10 plus h, like so. Okay? Times 4.9. So let's put the 4.9 on top. Forgot about that. Shame on me. Okay, so again, h and h cancel each other. So we can write right here, it would be the limit as h approaches 0. And this is the motivation to use h rather than, in this case, it would be x minus 5. If I use the original definition. What we end up having is the limit of 4.9 times 10 plus h. And of course, using the limit laws, 4.9 is a constant multiplier, and now I can have 4.9 times the limit as h goes to 0 of 10 plus the limit of h goes to 0 of h, and again this goes to 0, so I end up having 4.9 times 10 or 49, and this will be in meter per second. Okay, except I messed up. This is negative. Okay, this is negative right here. So forgive me for my oversight. There is a negative sign here, and this is negative. So it's negative. It's negative because the direction of the velocity is downward. So, and up, by our definition, up is positive, down is negative. So there is a negative all the way around. 49, because we have 10 right there. The limit of 10 is 10. Okay? And this is the same result that you obtain in the lab. You obtain it first numerically, and then you obtain it using this treatment. So basically I solve assignment 2B in front, so you can go ahead and make the necessary adjustment.